This is Lesson 6 in our Calculus 3 series, Planes. Planes are specified by a point on the plane and a normal vector to the plane. And that's a vector that is orthogonal to all vectors contained in the plane. So let's take a look at this sketch here. Let P0 be a point in the plane with normal vector n, which in component notation is ABC. So P0 is a point in the plane. From it we've drawn normal vector n in direction ABC. For any point P on the plane, vector P0P is orthogonal to vector n. Vector P0P is orthogonal to vector n. Well, yeah, because P0P is contained in the plane and n is a normal vector to the plane. So vector P0P is orthogonal to vector n. Well, that means their dot product is going to be 0. So vector P0P is going to be x minus x0, y minus y0, z minus z0. Vector n we said is ABC. And then P0P dotted with n is equal to 0 because they are orthogonal vectors. So their dot product, a times x minus x0 plus b times y minus y0 plus c times z minus z0 is equal to 0. And that is our equation of the plane through x0, y0, z0 with normal vector ABC. Notice that if we multiply out in this equation, we'll have ax plus by plus cz plus a negative ax0, negative by0, and negative cz0. These are all constant terms, and we can group that together and call it d. So if we multiply out, the simplified form for an equation of a plane is ax plus by plus cz plus d is equal to 0. And I want you to note that we can still read the normal vector off of this equation. A, B, C is that normal vector. Now looking at the same situation in vector form, we can find a vector equation of the plane. So we've got the same points P0 and P that are in the plane. N is a normal vector to the plane, and now we're looking at vector P0P, and we recognize that if we start out with position vectors R0 going from the origin to P0 and R going from the origin to P, that vector P0P is actually R minus R0. So we can say that R minus R0 is orthogonal to N. Their dot product is equal to 0. So in vector form, we get n dot r is equal to n dot r0, and that's the vector equation of the plane. Now let's find an equation of the plane perpendicular to 3, negative 2, 5, and passing through the point 2, negative 4, negative 3. Now I notice here they're asking me for an equation of the plane. The first thing I'm going to write down is the equation of a plane, and then I'm going to fill in what I need. I notice once I write this equation down, I need to fill in ABC, the normal vector, and x0, y0, z0, the point that the plane goes through. And that's exactly the information they gave us. They said this plane is perpendicular to this vector, which means this is a normal vector to the plane, and they gave us a point that the plane passes through. So here we have our ABC, here we have our x0, y0, z0, and so we just plug in and simplify. And so we have 3x minus 2y plus 5z plus 1 is equal to 0 as the equation of our plane. Now from back in lesson 4, we had an example, find a vector normal to the plane containing these 3 points. And in order to find that vector normal to the plane, we had to first create vectors, QP and QR, and then take their cross product, and that would be a vector normal to the plane. We found that vector to be negative 9i plus 5j plus 6k. Now we want to ask a little bit more. Let's find an equation of this plane. So again, we were originally asked to find a vector normal to the plane containing these 3 points. Well, now I'm saying let's find the equation of the plane containing these 3 points. And since they're asking for an equation of the plane, I write down the equation of the plane. And I realize what I have to plug in. I need an ABC, a normal vector to the plane, and I need a point, x0, y0, z0, that the plane passes through. From what we did in lesson 4, we found a vector normal to the plane. We found QP cross QR. That gave us negative 9, 5, 6. That's our normal vector. But we were given 3 points that this plane contains. So which is going to be our x0, y0, z0? Actually, it doesn't matter which one we choose. Choosing point P, we fill in our ABC and our x0, y0, z0, and we're here, and we simplify this down to negative 9x plus 5y plus 6z plus 3 is equal to 0. And actually, if you choose points Q or R instead, you'll see that in simplified form, it's exactly the same equation. So I'll leave that for you as an exercise. Now let's talk about parallel planes. Two planes are said to be parallel if their normal vectors are parallel. The easiest example to visualize, I think, would be two different z constant planes. So for example, we have z equals 4 and z equals negative 2. Intuitively, we recognize that these are parallel planes. Let's take a look at their normal vectors. For z equals 4, I want to recognize a normal vector in the direction of the positive z-axis, so I'm going to talk about vector 0, 0, 1. And for z equals negative 2, I'm going to talk about 0, 0, negative 1, the normal vector in the other direction, just to show that these two planes are parallel and they have parallel normal vectors. Now for a little bit more complicated of an example, let's take a look at these two planes. The forward plane, plane number 1, goes through the origin and has normal vector 2, negative 1, 3. So 2, negative 1, 3. And this plane goes through the origin. A parallel plane to it would be a plane through a different point, say negative 3, 0, 0. And normal vector that is parallel to 2, negative 1, 3. So here we have normal vector 4, negative 2, 6. So here this plane goes through negative 3, 0, 0, and it has a normal vector 4, negative 2, 6. And those planes are parallel. Intersecting planes. Like lines in two-dimensional space, planes have the property that if they're not parallel, they're intersecting. So if two planes are not parallel, they are intersecting planes. Their intersection is a line, and the angle between the planes, called a dihedral angle, is the acute angle between their normal vectors. So, for example, do these planes intersect? And if so, find the dihedral angle. Find the angle between the planes. So we've got these two planes, x plus 3y plus 2z minus 6 is equal to 0, and x minus y plus 2z minus 2 is equal to 0. We notice for plane number 1, we can read off our normal vector as 1, 3, 2. And for plane number 2, we can read off the normal vector as 1, negative 1, 2. And so these planes are not parallel because the normal vectors are not scalar multiples of each other. So that means they're intersecting planes, and we want to find the dihedral angle. We want to find the angle at which they intersect. And the angle between the planes is the acute angle between their normal vectors. So we need to find the angle between the normal vectors here. So we'll set up their dot product, and we'll be able to find cosine of the angle between them. n1 dot n2 is equal to length of n1 times length of n2 cosine theta. Length of n1 is 1 square plus 3 square plus 2 square, so that's radical 14. Length of n2, 1 square plus negative 1 square plus 2 square, that's radical 6. Their dot product is equal to 2. And so the equation we get for theta is here. And so theta is approximately 1.35 radians, or 77 degrees. Before we say that we completed the answer, we have to remember the definition of the angle between planes. It's the acute angle between the normal vectors. And notice that the 77 degrees here that we got is an acute angle. But notice if we instead had used normal vector -1, +1, -2, that's a vector parallel to this that would have also been a valid normal vector for this plane. If we had chosen that, then our dot product would have turned out to be negative, -2. And in that case, we would have had to take cosine inverse of -2 over radical 14 times radical 6, and that would have given us 103 degrees, which is not acute. So in that case, we would want to take the supplement of this angle, 180 minus 103, 77 degrees. And that would be the angle between the planes. Let's take a look at this example. Find an equation of the plane containing the line x equal 2 plus 3t, y equal t, z equal 1 minus 2t, and the point 2, 1, 1. Now the first thing I want to check here is that this point is not actually on this line, because I'm expecting that this is a line and then a separate point, and so that the answer to the question will be one unique plane that goes through them. So let's just take a minute to check that 2, 1, 1 is not on this line. How can we check, by the way? If 2, 1, 1 were on the line, we would need a particular t value that would make x equal to 2, and at the same time, the same t value make y equal to 1 and z equal to 1. So if x was going to equal 2, that would mean t would have to be 0. If t were 0, y would have to be 0, and that's not the same point that we're at. So in fact, this point is not on this line. We're not going to find a t value to make the xyz triple 2, 1, 1. So the plane that we're looking for is a unique plane. So anytime they're asking us to find an equation of the plane, I want to start by writing down the equation of the plane, and then seeing what I have to plug in. I need an ABC normal vector to the plane, and I need an x0, y0, z0 point on the plane. Well, I already know that 2, 1, 1 is a point on the plane. So we have x0, y0, z0, but we don't yet have a normal vector to the plane. Okay, let's think about what we do have. We have a point, and we have a line. We also know that we can get an orthogonal vector by taking the cross product of two vectors. So from this point and this line, can we create two vectors that are in the plane, that are not parallel to each other? So that when we take the cross product, we'll get a normal vector. And sure, we could take 2 points on this line and this point and create vectors. So I want you to please pause the video and start there. I want you to find 2 points on the line, meaning taking 2 separate t values to give you 2 different points on the line, and create vectors with the 3 points. Take their cross product, get yourself a normal vector, and you can fill in the equation of the plane. We were given point P, 2, 1, 1. And I noticed that when t is equal to 0, we get point 2, 0, 1 from our line. And when t is equal to 1, we get point 5, 1, negative 1 from our line. So I'm going to call these points Q and R, and I'm going to take a look at QP and QR as vectors in the plane. If we take their cross product, we're going to get a normal vector to the plane. So I take their cross product and I get negative 2, 0, negative 3. And this is normal to the plane. Now if you had chosen different points, the vector that you get might be parallel to this vector. So that might be a scalar multiple of this vector. And that's perfectly okay. Now as I did in a previous lesson, I'm looking for a vector that's normal to the plane. And I see that I've got a negative 2, 0, negative 3. Well, if I negate this vector, I'm taking a scalar multiple of it, I get 2, 0, 3. That's nicer. That's easier to deal with than having negatives hanging around. So I'm going to use 2, 0, 3 as my normal vector to the plane. So I've got my point 2, 1, 1, my normal vector 2, 0, 3, and our equation looks like this. 2x plus 3z minus 7 is equal to 0. And with your choice of normal vector and your choice of point, you'd get the same equation or perhaps a multiple of it. But if you simplify the equation, it would be exactly this. Now let's take a look at the distance from a point to a plane. So here's our plane with equation ax plus by plus cz plus d is equal to 0. And with that equation, we recognize that the normal vector is abc. And here's a point P1 not on the plane. It's x1, y1, z1. And we want to find this distance d. Well, we're going to consider a point in the plane P0, x0, y0, z0. And we're going to consider the vector P0, P1. Let's call that vector b. Then vector b has component notation x1 minus x0, y1 minus y0, z1 minus z0. And what do we know about the distance in terms of vectors n and b? We know that the distance we're looking for is going to be the length of the projection of b onto n in absolute value. So notice if we project vector b in direction of vector n, we're going to get the distance that we're looking for. So we want the component of b along n in absolute value. That's the distance we're looking for, the scalar projection. So our formula from lesson 3 tells us that the component of b along n is n dot b over length of n. We want it in absolute value, so we're here. Now notice if we expand this to simplify, we're going to have ax1 plus by1 plus cz1 minus ax0 plus by0 plus cz0. x0, y0, z0 is on the plane. So ax0 plus by0 plus cz0 is equal to negative d. So all of this can be replaced by negative d, and we get then a plus d here. So this is our formula for distance from a point to a plane. So for example, find the distance from point 105 to the plane 2x plus 3y minus z plus 6 is equal to 0. Essentially what we're doing in the numerator here is plugging this point into the left-hand side of the plane equation. So we have 2 times 1 plus 3 times 0 minus 1 times 5 plus 6, all in absolute value. And we want the length of the normal vector to the plane in the denominator. The normal vector is 2, 3, negative 1. So its length looks like this. And we get 3 over radical 14. And that's our distance. Let's take a look at another example. Where does the line through 101 and negative 302 intersect the plane x plus 2y plus z plus 5 equals 0? Well, if we had parametric equations of this line, then we would be able to represent x by a function of t, and y by a function of t, and z by a function of t, and then we could just solve for t. So that's our plan here. We want to find the equations of the line between these 2 points. So using these 2 points to find a direction vector for this line gives us direction vector 4, 0, negative 1. And here I've set up the parametric equations that use the point 1, 0, 1, 1, 0, 1, and use the direction vector 4, 0, negative 1. So now we have a parametric representation of the line, and now we can substitute 1 plus 4t in for x, 0 in for y, 1 minus t in for z. Because what we're saying is that if this line and this plane intersect, there's got to be a t value for which these coordinates fit this equation. right? There's got to be a point on the line, so there has to be a t value for which these xyz coordinates fit the plane equation. So that's what we're trying to find here. So we set x equal to 1 plus 4t, y equal to 0, and z equal to 1 minus t, and we solve for t. We get t is equal to negative 7/3. Well, that doesn't answer the question quite yet. We were asked at what point the line and plane intersect. So we need to take our t value and plug them in and find x, y, and z. And we find that that point is negative 25/3, 0, 10/3. And this concludes our lesson on planes.